Hello, welcome back. There were actually two handouts today. They were stapled together. The handout number 17 and 18. One of them was the solutions to the homeworks, which you should have turned in today. That was handout number 18, was the solution to homework number 3, which if you haven't already, you should put up in the pile over here. The other staple to that was handout number 17, was the sample midterm. And some of the handouts, one was in front and the other was in front. So don't take two because they're the same, even though the order may have been different. Now, unfortunately, we didn't get those handouts into the SITN distribution facility in time for the people watching on television to have gotten them. It is in the pipeline now, so to speak. And we hope that you will be getting it momentarily. It may not happen tomorrow. It may, in fact, happen on Monday. However, you can certainly come pick them up in the office this afternoon. The other thing is that tomorrow there will be a double-length review session for the midterm, which is next Tuesday, you all know, starting at 10 o'clock in Skilling 193 upstairs, and people from SITN can watch in and see some of the material that is described in those handouts being gone over. So if you don't have the handout in front of you, it won't be a terrible tragedy. You can also ask questions. Yes, David?
Okay, the sample midterm and a clean version of the sample midterm are both available online in the handouts directory. So if you don't have one and you're out in SITN, you can FTP to Stanford and pick up those. Also, the solutions will be available online after class today, and not until then because we haven't turned things in. So probably at 5 o'clock. And again, if you don't get them at your site, you can get them online, FTP them.
Thank you. By a clean version of the midterm, you mean a version without the answers, so you don't have to hold your hand over the answers while you're trying to answer it yourself. Somebody wanted to make an advertisement today, an announcement about an upcoming event this evening. Why don't you come describe that?
Do we have the overhead camera, please?
Can you use the microphone?
Sure. Tonight, the IEEE is having a guest speaker. Dean Brown, the founder of Zilog Corporation, is coming. It's at 5:30 in Terman Auditorium, and we will be serving refreshments and pizza, as usual. So please come. It should be a very interesting talk.
Thank you. I'm going to go to that. It sounds like it should be fun. Speaking of old-time stuff, I have something to give out today, or to hand around here at least. We're going to get into talking about a particular kind of scheduling mechanism that was used first in the Control Data 6600 computer, which was out in early 60s, 63, I think, something like that. And I have actually the original reference manual for that machine, which I'll pass out here for you to amuse yourself with, including the picture of, remember what Seymour Cray always used to say was the most important part of computer design, which is the plumbing. And if this looks like the back of your refrigerator, it's not. This is the CDC 6600 cooling system, Freon refrigeration technique. But the rest of this book also describes lots of other interesting features about the machine, including an algorithm which we'll be discussing, which is still in use, and lots of other innovative techniques in this machine. It was a multi-processor machine with one main processor having the scheduling algorithm we're going to be talking about, but in addition had 10 peripheral processors, which were basically hardware time-shared. The peripheral processors had one ALU unit for all of the computers, so to speak. It was really 10 computers in one, and a big barrel shifter for all of the state information for all of the 10 computers. So it would execute one instruction using the ALUs and the mechanism of the CPU for one computer running one program, and then it would essentially shift the barrel one position, changing all of the registers for the next instruction to the next computer, and then execute one instruction of that next computer. So it was a way basically of doing hardware time sharing on an instruction by instruction basis to save the cost of additional ALUs and additional hardware. Very clever technique, which is no longer used. However, the scheduling system, the scoreboarding system that we'll talk about, is something which is still used. Okay, last time we were talking about, or started talking about, what do we do if we're trying to elaborate our DLX pipeline to do run-on instructions, which is to say instructions that take multiple cycles in execution instead of just one. And the example pipeline here was one where integer instructions took a single cycle, as we saw before. Multiplies, integer or floating point, take a total of 6 cycles, and it's partially pipelined in the sense that the first stage is busy for 3 cycles, and then that instruction moves on to the next stage, and another instruction can enter that stage 3 cycles later. So for the multiplier, the latency is 6, the time it takes from input to output, and the repeat rate is 3. And so on for the other execution units that we talked about before. But now, because we've done this, we've got all kinds of problems, which we didn't have before. We now have structural hazards, which we didn't have before, because units are not fully pipelined. When you're about to issue another instruction, and that multiply unit is already busy, you can't issue the next instruction. It basically has to stall waiting for the functional unit to be busy. We also now have write after write hazards, which we didn't have before, because short instructions may be finished and ready to write back to the register file before long instructions that started before them. So if you do that, you might wind up, in fact, writing things in the wrong order. Question?
Is that just one ALU doing all those operations, or can I put an integer add through and also a floating point multiply? If there's a floating point multiply being worked on.
Yes, all 4 of these things can have something in them at the same time. So the structural hazards are for a particular unit. If you've got a divide somewhere in this divider, you can't issue another divide. But if the floating point adder is free, you can issue another floating point adder. So in fact, you've got multiple units in execution at once. So we have write after write hazards. Notice that we still don't have write after read hazards. And that's because we're still issuing instructions in order, and the register reads always occur early in the instruction. The only way we could get a write after read hazard would be to have some instruction which reads late in its cycle, and another instruction issued after it which writes earlier on. And then this write occurring after this read will occur in the wrong order, in the sense that this read will get the result of this write rather than the original result. So we don't have this yet, although as we elaborate our machine to allow instructions to be issued out of order, we'll eventually discover that we have write after read hazards. And of course, as we talked about last time, we now have interrupt headaches because the instructions may complete out of order. So if instructions I+1 and I+2 are already finished, but a previous instruction I is the one that causes an interrupt and has to be restarted, we've got a problem. We have to deal with it. So how do we solve those problems? Well, before we solve them, let's just take a look at some of the examples of conditions where, for example, we have structural hazard. We might have a structural hazard, in fact, for the write-back stage, and I've marked this as write-back F under the assumption that the floating point registers and the fixed point registers are separate. That may buy us something, at least, because we can do a fixed point write-back and a floating point write-back at the same time, but it really doesn't help. I mean, here's a case where we start a multiply, and it's going to take 1, 2, 3, 4, 5, 6 cycles. And in the next cycle, we try to start an add, and it's going to take 4 cycles. I think, in fact, there's some discrepancy between this chart and the previous one. Yeah, in the previous one, I showed the latency for add as 2 cycles and the repeat rate as 1. So here we've changed the assumption slightly, and at this point, for this chart, the latency for adds is 4 and the repeat rate is 2. And the latency being 4 means it spends 4 of its cycles in execute. And notice, of course, that it's ready to write back to the register file before the instruction which follows it. And notice, in fact, that there's no conflict because they're writing back to different registers and there are no data dependencies between these 2 instructions. So this is a safe thing to do. The only problem with this is not a hazard, but an interrupt recovery issue. What if, in this case it probably can't happen, but what if this one had completed and this one interrupts? So this represents a problem in recovering from interrupts. This represents a structural hazard, assuming that the floating point register file only has one write port, we can't do both of these in the same cycle. So how do we resolve or avoid those hazards, structural hazards, for anything, for registers being written back or for functional units that we need? Well, one way to do it is to have a shift register, basically a table that indicates for each functional unit or register file or resource which may be under contention, where in the future that unit is going to be used. And I think the now here is actually off by 1. You can check that yourself later. But basically, if this represents now, a 1 bit over here means that in 1, 2, 3, 4 cycles later, whatever unit this is, let's say it's the floating point write-back file, is going to be busy. For each instruction type that you want to issue, you have a mask that says, if you were to start in this instruction now, when is it going to need that resource? When is it going to need that write-back slot for the floating point register file? Well, in the case of multiply, let's see, if I start counting from here, that says that 1, 2, 3, 4, 5, 6, 7, 8 cycles later, it's going to need the write-back file. Well, basically, you just look to see whether in this position of the current reservation mask there's a 0. If there is, then you know it's safe to issue that instruction. You can set that bit on, indicating that that slot is now reserved, and issue that instruction and start it in execution. If that bit were already 1, then you know that some other instruction somewhere in its execution phase has decided that it needs that slot, and you need to delay issuing the multiply until you get a 0 in the position where it wants to do the write-back. So each cycle, as execution proceeds, you simply shift this register 1 to the left, and any instructions which are awaiting to be issued, waiting to begin execution, can compare their reservation mask to the current state of the shift register.
So then, if it's okay, you can just OR the two together to get the...
That's right. If it's okay, you can just OR the two together, and that sets the reservation bits on. And in a complicated scheme that, in fact, requires multiple cycles in a particular unit, there may be more than 1 bit on in the reservation mask. You've got to make sure that all the bits you're about to OR on are 0 in the reservation table so that you get simultaneous reservation for all of them. Now, this is one technique, and it works. Notice what happens, though, is that we're stalling very early. We're not beginning the instruction if we think that later on it's not going to get access to the resource it wants, like the register write-back file. An alternative is, an alternative to delaying the issue is to issue it if the immediate resource it needs is available. If it needs a floating point adder and it's got a floating point adder, you could issue it now and defer until later what happens when you reach a unit that requires a conflict. This can also be done. In fact, this is done in a scheme we'll see later, but it has some other complications, including the fact stalls then can trickle back to block earlier stages. You've got this instruction which is now in floating point add trying to get out to do a write back, and there may be another instruction waiting to get into floating point add, and you've just backed up the pipe, causing other instructions to stall in the middle. But that kind of scheme can also work. Okay, what about data hazards? Well, we still have read after write hazards, and we can solve them in the usual way we did before. We simply install the instruction issue until the source registers can be forwarded for use by that instruction. I convinced you, I think, that read after write hazards can happen, but we do still have sort of pure write after write hazards. 2 instructions, both of which update the same register, like these. And in this case, divide is likely to finish second, subtract is likely to finish first, and you wind up with, eventually, the result of the divide being left in F0 instead of the result of the subtract. Well, one possibility is, if you look at this instruction sequence, is to say that's a ridiculous piece of code, because why did you bother to do the divide to begin with if you were going to about to overwrite it with a subtract? And since it's a piece of code that doesn't make any logical sense, we have the right to execute it incorrectly. Well, that's probably philosophically an unacceptable thing to do. The other observation is that although it looks like a useless sequence, in fact there are times when sequences like this might occur. And one example is if this instruction happens to be in the delay slot of a branch. And in one or the two conditions, if it branches or it doesn't branch, in fact, the sequence doesn't make any sense. But in another of the two sequences, if it branches or doesn't branch, it may in fact make sense, and you need the result of the subtract f. So you can't execute, even though this looks like a nonsensical sequence of instructions, you can't produce wrong results. So there are basically two choices. One is that you can delay the subtract until its write-back stage happens after the write-back stage of the divide, and that'll get the results occurring in the right order. Or in fact, you can detect that this is happening and that there's a second write to F0 with no intervening read, and then you can just no-op the divide. Or at least no-op its write-back. I guess you could argue that if you turn the entire instruction into a no-op, and if it's an instruction that would have interrupted, that if you turn the whole thing into a no-op, you're not getting the interrupt, and therefore you're not obeying the semantics of the program. So probably the safe thing to do is to turn the write-back into a no-op, not the divide instruction itself. Now, notice that this is a kind of pure write after write hazard. If there were an instruction in between that actually uses F0, then it turns into a read after write hazard, and the instruction that uses F0 will stall, and the instruction following it, therefore, will also stall, and the write after write problem, as described here, doesn't occur. Okay, so that's data hazards with run-on instructions. Now what happens if we get interrupts? Well, here's an example of a situation which could cause a problem. Let's say that we have a divide instruction that starts, and it's a long-running instruction. And it's followed by a short instruction that, in fact, destroys its operand, and then followed by another short instruction which interrupts. Well, if this causes an interrupt, then the divide instruction may not be finished. So, in fact, if you take the interrupt then and suspend the divide instruction, when you resume, you may have to resume the divide instruction. Also notice that the add destroys its operand, so in fact you can't re-execute the add instruction without producing incorrect results. There are lots of other combinations of long and short instructions where no matter how you figure out where you're going to take the interrupt and suppress instructions or not suppress instructions that are in execution, you wind up with a difficult state to reconstruct when you try to resume execution after the interrupt. So what do we do? Well, what used to be popular to do, in fact, is to ignore the problem and to say that if you get an interrupt in a condition like this, that basically it's an imprecise interrupt, and you do not allow that instruction sequence to restart. The 36091 did that, the Cray machine did that. Basically, you get an interrupt that says your program has done something bad. Number one, I can't tell you exactly where it happened, but it was someplace in the vicinity of these instructions. And number two, there's no hope to be able to restart the program. Now, some people are willing to put up with that in favor of getting blazingly fast execution speeds. Some people are not. In particular, the definition of IEEE floating point standard these days requires that floating point interrupts be precise. So machines that only have imprecise interrupt modes, especially for floating point operations, are probably not going to get built much anymore. Well, what can we do to help it a little bit? One possibility is to allow the software to decide where the restart points are, to basically provide an instruction, and the DEC alpha does that, called trap barrier, that basically marks a point at which all prior instructions are guaranteed to commit and to execute without interrupts. So basically it allows you to establish a point at which all interrupts can occur, and interrupts following that will not disrupt the previous instructions. That's one possibility. Another thing you could do is to record when an interrupt occurs enough state information to say which of the combination of instructions actually has completed. You could record multiple program counters and indicate which instructions have completed, which instructions have not completed, and in order to return from the interrupt, the software could manually, so to speak, re-execute those instructions that have not been executed, skipping over ones that have been executed. It becomes even more complicated when instructions can be partially executed, and they may have partially updated register results, and you have to simulate the completion of the second half of the instruction. Another approach, which both some of the versions of MIPS and Pentium do, is to try to figure out ahead of time whether an instruction is going to cause an interrupt. And if it's not, you can issue it and have it execute in pipeline fashion and finish before previous instructions. But if it looks like there's a possibility that that instruction might cause an interrupt, then you delay issuing it until all previous instructions are known to either be finished or not cause an interrupt. Now, on the face of it, that seems like a difficult thing to do, because you would think that you'd have to execute the instruction in order to be able to figure out whether it's going to cause an interrupt. But in fact, there are lots of cases, in particular in floating point arithmetic, where you can make some rough tests to see, is it possible at all with these operands, only by looking at a few bits of the operands, for this instruction ever to cause an interrupt. And if the answer is no, then you know you can issue it. If the answer is yes or maybe, then you can delay the instruction. So it doesn't have to be a perfect test. You can use a test which has a false positive that says that the instruction might interrupt, whereas in fact it won't interrupt. You take a bit of a performance hit, but at least you know that if an interrupt occurs, that you've made it such that the exceptions occur in order. None of these are great solutions. And the great solution is, even though you've got instructions executing in parallel and completing out of order, you'd like to be able to make the interrupt perfectly precise without any software headaches. And in fact, there are several different ways to do that. They all require adding additional hardware so that you can produce, when the interrupt occurs, a correct register set that represents all the instructions prior to the interrupting instruction having finished, and all of the instructions following the interrupting instruction to have had no effect. So let's look at a couple of different ways that one might design hardware to do that. Probably the earliest technique for doing that is basically every time you write a result to a register file, in case you have to undo the effect of that instruction, you save the old value of that register. So you have a history file which saves old copies of registers that may be needed to essentially unexecute the effect of an instruction because some previous instruction has interrupted. And then when you are about to take the interrupt, you have to go through this history file, figure out which ones need to be reapplied, and restore those registers back to the register file. In the meantime, if you're not doing any taking any exceptions, then results are written to the register file, and operands sent to the ALU are taken from the register file in normal fashion. And notice you might also need to do this history for memory writes as well as for register writes, because you may have to undo some memory writes as well. This obviously is a complicated thing to do, and this process of restoring the appropriate destinations is complicated to do. But there are machines that have done it. Some of the early CDC cyber machines did it. I think some of the VAX implementations used a version of the history file to undo instruction execution when an interrupt occurs. Another approach is a reorder buffer. Basically, this says that you don't ever write results to the register file except in the order in which the instructions originally appeared in the instruction stream. And basically, the reorder buffer is a set of entries that are ordered, that are allocated in order in which instructions are issued. Let's take a look at what a reorder buffer might look like. Each entry in the reorder buffer would need to have several fields. One is a field that says whether or not this instruction is accepting whether or not this is an instruction that is causing an interrupt. So there's some status bits. You also need to record the program counter of the instruction so that you know if an interrupt occurs where the restart point is. You need to store the destination register number for that particular instruction and the value, which is to be written into the register file when that instruction completes. And basically, instruction I gets a slot here, instruction I+1 gets a slot here, instruction I+2 gets a slot here, and so forth, and each of them has its own destination register file designator. And as the instructions complete, rather than updating the real register file, they update their value in the reorder buffer. So this one may already be written. The preceding instruction may still be executing and there may be nothing in its value field. This one doesn't get written back to the register file until this one has written its value and is completed and is not causing an interrupt. And basically, as the top element in the stack is finished, as its instruction execution terminates and its value is available, that entry gets purged. This value gets written into the register file. If it's marked as an instruction which is causing an interrupt, the interrupt is taken at that time. All the instructions ahead of it, which have already finished, never write their results to the register file because they're in the reorder buffer, they're not in the register file. So the registers are updated and the exception status is tested in the order in which the instructions were originally issued, regardless of what order they complete and produce their results in. Make sense? Well, that all works great. The only minor complication with that is that now we've got more data hazards because we've got all of these result values that are not in registers, even though instructions have completed, that are sitting in the reorder buffer and not in the register file. So in order to make subsequent instructions work correctly, we need to forward results now, not only as we did before, but also out of the reorder buffer. And in fact, it's a more complicated kind of forwarding than we did before, because there's no one place you can look at to see whether a particular register is in this reorder buffer. You've basically got to do an associative compare or scan all of the destinations in the valid entries in the reorder buffer to see if any of them represent the register that you need for a new ALU operation. So this requires lots of hardware. It requires lots of ports and ports to be able to read things from the reorder buffer and comparators to be able to check the currently issuing ALU operation to all of the possible destinations. Notice that the same register may appear multiple times in the reorder buffer. So if you have multiple hits with that destination register, you also have to pick the correct one. So as a way of simplifying the hardware necessary for a reorder buffer, we can elaborate it just a little bit more. We can do the same thing we did before. We can have a reorder buffer that keeps things going into our register file in issue order, in the order in which instructions were issued. But in addition, we can have another completely duplicate register file which writes the results as they are available and as they complete. So in fact, rather than searching the reorder buffer to find the appropriate operands to forward to the ALU, we can directly access the register out of the future register file. These are the values that will eventually be in the register file as instructions complete in order. But they're available here out of order for sort of random access by operands to ALU instructions later. Well, it's a trade-off, because this results in fewer comparators. In order to do the forwarding here, you just do a direct, well, it's the normal forwarding we did before, plus a direct lookup in the future register file for results which are in registers. So there are lots fewer comparators. You don't have to do this associative search for all the registers in the reorder buffer. The disadvantage is that it duplicates the register file. If you've got 128 registers in the architecture of your machine, now you have twice 128 registers stored in the processor as a whole. And notice that the sequential register file is kind of useless, except in the case where an exception occurs and you're trying to back out of instructions that shouldn't have been executed when the exception occurs. Reorder buffers are certainly in use. In fact, I guess the PowerPC 604, one of the latest PowerPC processors, uses a reorder buffer. I'm not sure whether or not it uses a future register file, but they're equivalent, and they can make the trade-off based on how much.
Hello.
Yeah?
Question here.
Yes?
Could you go back to your previous slide, the first one which you showed about interrupts coming in?
Yeah?
No, the one before this.
I'm not sure how far back you want.
Yeah, this one, right.
Yeah.
Right. So I think the whole discussion you're having here is because when an interrupt comes, you want to flush the pipeline at that point, so you're not sure what register values have been written by which instruction. Is that so?
The problem is that when an interrupt occurs, like on this instruction, subsequent instructions may already have executed. Some of them may have executed and updated their results. Some of them may not have executed and updated their results. So how do you get back to a point where it's easy to restart that program? Well, one way is to essentially make the effect of subsequent instructions disappear, to restore the registers that they are writing back to their original state before the divide occurred. And that's what the purpose of those reorder buffers are.
Okay, right, thanks.
Okay. So that's how to get interrupts and exceptions to be rational, even in the case when instructions are completing out of sequence. And that basically ends chapter 4 of the book on basic pipelining, although I guess you could argue that some of it was not so basic. But now we're starting to move into chapter 5 of the book, which talks about ways to make machines even faster, both from a software point of view and from a hardware point of view. This is stuff which is not covered on the midterm, by the way, so anything from here on you can enjoy for the final later. So let's review our pipeline processor in terms of performance and see where it is we're taking hits. Well, the ideal CPI is basically the number of pipeline stages, or reduced by the number of pipeline stages, but we have to add to that structural stalls that come from resource conflicts, control stalls that come from branch delays, read after write stalls, which are the true data dependencies, the ones that you sort of can't do anything about because it's one instruction which depends on a previous instruction for its value. So these are real stalls or real issues that you have to deal with. Write after read stalls and write after write stalls are so-called name dependencies, where the only reason that that's causing a problem is because the register got reused. You're writing into a register that previously may be in use. If you had chosen a different register, the program would still work, and in fact you could remove that stall or remove that dependency. And we'll see both software and hardware techniques for basically making these name dependencies disappear, because they're not fundamental to the program. They're sort of artifacts of the fact that we have a limited number of registers. So in reducing these things, we have both hardware and software tricks. The software can do scheduling based on what it knows about the pipeline. It can do loop unrolling, which is a technique we'll see in a second, in order to mitigate the effect of branch delays. And it can do register renaming to solve the problems I was just talking about, the fact that we've reused a register where in fact we might have been able to use a different register. But we're not out of tricks in the hardware domain either. We can do dynamic scheduling. Right now we've had pipelines which only issue instructions in the order in which they occur in the original instruction stream. There's no reason to do that. We could in fact even issue instructions, get them started in execution out of order. That's got some problems, but it also has some performance gains. We can still do better at branch prediction. We tried to do some clever things earlier on, and we did, but there's more we can do in terms of refining our estimate of which way the branch is going to go and be able to get better performance because of it. Then there are several other techniques for issuing, not only issuing instructions out of order, but in fact issuing instructions simultaneously. You might do 2 or 3 or 4 or 8 instructions and get them executing all during the same clock cycle, rather than dispatching one at a time, one in each clock cycle. And then there's speculative execution. we're trying hard to get a good estimate of which way the branch is going to go, but there's a limit to how far we can take that. One of the things we could choose to do, in fact, is to go down both paths of a branch, or in general use other techniques that allow us to start executing entire sequences of instructions that we may have to cancel. Not in the previous case because we took an exception, but in this case because something else happened, because a condition resolved itself that said that we really didn't want to execute that instruction stream, erase it, make it go away. And if we have enough hardware to devote to doing that kind of speculative execution, we may be able to increase performance quite a bit. Let's take a look at some of the things that software can do. This is a simple case of discovering parallelism within loops. Let's say that we had a program that simply added to the vector b a constant c and stored the result in a. Now notice that every iteration of this loop is independent of the iteration before it. There's no references from I to I plus 1 or to I minus 1 or to any other elements of the arrays. So there are no loop-carried dependencies, and we'll see an example of loop-carried dependencies later on. But because there are no dependencies, it means that we could arrange to execute multiple bodies of this iteration simultaneously without causing any problem. Well, let's look at the first attempt that a reasonably clever compiler would make to execute this code. We've seen things like this before, so it's fairly straightforward. If register 1 is pointing to array B, then we load an element for register B into F0. We add it to C, which we preloaded into F2 as a constant, stored in a register. We store the result into 0 of R2. R2 points to the array A. Then we increment our 2 pointers by 8. In this case, these are double precision floating point values of 8 bytes each. And then we check to see whether one of those pointers has reached a pre-computed end value. And if it hasn't, then we go around and do the loop again. I'm only showing the body of the loop. I've avoided showing the initialization that sets up all these pre-computed values, but I think it's pretty obvious what they do. And notice that we're assuming that this particular instruction set has a branch, conditional branch that allows you to compare 2 registers for less than or greater than and loop on the result. That doesn't happen to be true for DLX, but assume it for the moment. Well, how fast does this run? Let's make some assumptions about the operation latencies for each of these instructions. Let's say that the load takes 2 cycles, the floating double add takes 4 cycles, the branch takes 2 cycles, and otherwise there's a single cycle for execution. So in this case, we've got the load. Since the subsequent instruction is using the result of the load, we've got a true read after write dependency here, and we've got to stall the load instruction 1 cycle in order to be able to use the result. The subsequent instruction also has a true read after write dependency on F4. Remember, this is a store, so this is F4 is a source operand, not a destination operand. So we've got to give the add its 4 cycles to execute, which results in 3 stall cycles before we can store the result. The adds and the branches have no problem whatsoever. The adds at least execute in a single cycle. The branch has a single delay slot, which causes a stall because we've not put anything in it, representing a total of 11 cycles per iteration. Now, in fact, if the compiler were to know more about the pipeline of the machine that it's going to be executing on, it can do a better job just by reordering these instructions. And here's an example of a clever compiler having done that. Well, it loads as before, and in fact it adds as before, but rather than doing the store of the result as soon as the add is done, it pushes the stall down as far as possible. In fact, as far as possible here is down to the delay slot of the branch instruction. And that has essentially removed or hidden the 3 cycles of delay, which appear here, for the add double instruction. So we were left with only 1 stall instruction, and now we're down to 7 cycles per iteration instead of what did we have before? 11. Significant improvement just by reordering things. By the way, why couldn't we fix this? Why couldn't we take this add instruction After all, we're finished with register 1. We've already done the load, started the load for it. Why couldn't we remove that stall by moving the add up until that stall slot? Wouldn't that make it take 6 cycles instead of 7 cycles?
You'll still need a stall for the add D.
I only heard
for the F4, you still need 3 cycles for that to complete anyways.
Exactly. If you do that, then you've taken away one of the 3 instructions that you were using to hide the 4-cycle stall for add D. So if you move this up here, you just wind up pushing the stall further down in the loop. So basically, by rearranging instructions, there's no way to remove all of the stalls in this loop. But there is a way that we can remove all of the stalls in the loop. And that is by loop unrolling. Basically to recognize that we can do 2 iterations at once by doubling the amount of code inside the loop and then doing 1 branch. And we do that as follows. We start loading A sub 0, let's say. Am my notation right? Is this A? B. We start loading, oh, there it is, B sub 0. And before we use it, we start executing an instruction from the second iteration of the loop. We start loading B sub 1, which is 8 bytes away. Right? That has filled up the load delay slot for the first load. So when this is done, or after this has issued, we can now execute the add double for the first F0. And we've separated this read after write hazard by the single cycle necessary to avoid stalls. We can do the same thing for the next add. And now both of these adds can proceed down the pipeline. I'm assuming here a fully pipelined floating point add unit. And while they're executing, we can do the increments of the destination, of the array pointers. And notice that we're incrementing by 16 here instead of 8 because we've essentially done 2 iterations in 1. We've processed 2 members of each array. By the time we're down here, this first add is done. It's had its 3 cycles of delay, so we can do the store. And notice we've already incremented R2, so we've got to sort of look behind it and store 16 bytes before it to store A sub 0, the first result. And now we can do the same trick we did before. We can do the branch less than, and in the delay slot of the branch less than, we can execute the second store. And the second store is storing A sub 1, the second element of A, which is now 8 bytes behind where its register pointer has been updated to. So basically we're down now to 9 cycles per loop, but each loop does 2 iterations of our original program. So we're down now to 4.5 cycles per iteration. So we've gone from 11 to 7 to 4.5 just by beating on the guys over in the compiler department to do better code generation. Now, one of the disadvantages to this technique is we wound up using up more registers. This loop now uses probably twice as many floating point registers, or at least 1 times as many as it did before. But we're gaining an advantage 2 different ways. One is we've got more instructions to be able to shuffle around. Before, we sort of ran out of instructions to insert between read after write hazards and had to take a stall. Now we have more instructions to be able to play with and try to remove the stalls, and in fact in this case we removed all the stalls. The other advantage is that in fact we're only executing 1 branch instruction for every 2 iterations of the loop, rather than 1 for every iteration of the loop. So we essentially divide in half the amount of time it takes to do branches for the entire execution of the loop. Now, you don't have to stop at 2. You can unroll this as many times as you like. After a while, since we've already gotten rid of all the stalls, you can't do any better for that. Every time you unroll it another time, you save another branch instruction, so you're marginally getting execution time down. Of course, you're enormously expanding the size of the code. The other thing you have to be careful of in doing loop unrolling is that if the loop count is not known at compile time, and here it was, we knew we were going to do 100, but if loop count is not known at compile time, you've got to be real careful starting and ending these unrolled loops. Let's say that the loop, instead of being done 100 times, was actually being done 99 times. Well, you can't do this loop 50 times or 49 times in order to be able to get 99 effective executions. So you've got to do something clever by either doing one iteration before or after in separate code, or sometimes, in fact, you can manage to start the loop by branching into the middle of it, so you only do half of it the first time, and then after that you do it multiple times. It begins to be a challenge for the compiler. But still, it's a widely used technique, and those of you who want to know more about that sort of stuff can certainly take the compiler optimization courses in CS, like I think it's CS 243, which talks a lot about this and many other fancy techniques for doing optimization. Just wanted to show you what I meant before about loop carry dependencies, things that make that kind of loop unrolling more difficult. In this case, we're adding elements of B and A, but storing them in A of I+1, in the next element of the array. So each iteration depends on the iteration before it. You can't get two iterations going in parallel, because you have what amounts to a read after write dependency. It's a read after write dependency through memory, but still it's a dependency that you have to take into account. Loop unrolling still helps, because you still get the effect of reducing the number of branches, but there's not as much opportunity to produce parallel, to take advantage of parallelism because of these read after write dependencies from the code of one iteration to the code of the other iteration. I think this I won't go through in detail. I just wanted to point out, and the book shows some examples too, that things that may look like loop carried dependencies, and if you took a quick glance at this, it sure looks like things in loop I+1 depend on things in loop I, and we can't execute this loop in parallel. But in fact, if you're a little bit clever about starting and ending conditions and rewriting some of these indices, you can rewrite it in a form which in fact has no loop carried dependencies at all. And the textbook goes into techniques for doing this, and greatest common divisor, algorithms for determining when this is possible or not. And I think that probably deserves to be in a compiler course and not in a computer architecture course. So don't have to read that part of the book. Okay, I alluded before to this issue of write after read hazards and write after write hazards being avoidable. They're not fundamental to the execution of the program, and I just wanted to show you an example of it and how one could fix it in software, mostly because we're going to see examples later of how we can do essentially the same thing in hardware rather than software. Let's assume that we're executing on a machine that in fact allows you to execute instructions in any order as long as you don't violate read after write conflicts. So let's say that we have this divide instruction which starts up. It's going to take a long time, and it's going to produce a result in FP1. In fact, this instruction, this is a bad example, but let me make it more realistic. This instruction may not even be able to start because it may depend on some previous operand like FP2, which is not ready yet. And let's say that the subtract instruction can start, and in fact it's going to write FP2. Well, you can't do that because we've got a write after read hazard on FP2. Divide may not have started yet and have not gotten to read its FP2. If you execute the subtract and have it complete, then FP2 has been destroyed, and the divide will get the wrong result. Well, there's no reason for this, because if you had chosen to use a different register other than FP2 here, then you wouldn't have that dependency. In fact, this shows that by substituting for FP2 in the second and third instructions, FP5, you could get the subtract and the store to start executing, even though the divide couldn't yet execute. Now, obviously, all instructions subsequent to the subtract that depend on FP2 or that use FP2 have also to be rewritten to use FP5. So this reduces stalls on some pipelines where in fact the subtract can get started ahead of time, but in fact uses up additional registers. So your architecture needs to have been designed with enough registers visible to the programmer to allow you to do this. The hardware technique we'll see a little bit later shows that we can do the effect of this without actually having programmer visible registers in the instruction set. Okay, so let's start talking about some of these cleverer techniques to get more multiple instructions to be executed in parallel. So far in our pipeline, if an instruction stalls, everything after it stalls too. If there's some reason, let's say a read after write hazard or a structural hazard, that we can't issue a particular instruction, every instruction after that can execute. Even though it may not have a structural hazard, all of its results may be available in registers, it could go, but the way our pipeline is designed, we don't let it go. An example of that is here, where this subtract instruction could execute. It doesn't depend on anything in previous instructions, but we can't issue the add instruction because it has a read after write hazard on FP0. So add is waiting for divide, subtract is waiting for nothing. Why can't we just issue it? Well, that's the modification we want to be able to make to our machine. We want to be able to issue instructions and have them execute in any order. There is, unfortunately, a terminology issue here. It's like exceptions versus traps versus interrupts. People don't use terminology consistently. And in fact, I probably haven't been using terminology consistently even so far. What I'd like to do is start using it a little more systematically and say that instructions are issued at the time they are decoded and scheduled for execution. But in fact, they can begin in execution, which is to say be dispatched, out of order. And we're going to look at two different ways of doing that. Basically, there has to be something inserted in between the instruction decode and the beginning of execution that allows a bunch of instructions which have already been decoded to hang around in some data structure somewhere, waiting for all of the right conditions for them to be executed. And in fact, any one of them, in any order, can begin the march down the rest of the pipeline toward execution as soon as their operands are ready and as soon as all the structural hazards have been cleared, even though instructions before them are waiting for something else. Basically, this represents a pool of instructions that have been decoded and are eligible to execute as soon as they can go ahead. And there are two historical approaches to doing this, both of which are in fact having a resurgence these days as microprocessors become complex enough to allow this kind of dynamic scheduling. The scoreboarding one is the one we'll look at first, and that was done in '63 with the 6600, and that's the book that's circulating around. And then another one that was done several years later by IBM for the 31691 called Tomasulo's algorithm, and it has certain other advantages. So let's look at scoreboarding first. Basically, the idea in scoreboarding is that we keep things relatively simple. We have a register file. We have multiple functional units, some of which may be identical, some of which may be different for floating point adds, fixed point adds, divides, and so forth. And all of the functional units talk to read their operands from and send their operands back to register file. The scoreboard is basically a control unit that contains no values. It doesn't contain any of the register values. It just contains information that describes several things. One is it describes all of the instructions that are decoded and awaiting execution or currently being executed by functional units. It describes the functional units themselves. It keeps track of their status and whether there are instructions in them and what state they're in. And it also keeps track of destination registers. So it's a centralized way of managing all of these resources and checking for hazards. So in fact, the scoreboard you can view as a pipeline stage in between instruction decode and register fetch. It's a little bit funny to call it a pipeline stage because in fact multiple instructions can be in this stage at once. This represents that buffer I was describing of instructions that are decoded and awaiting assignment to functional units. Well, for the scoreboarding scheme, basically instructions don't get into the scoreboard until in fact there are no structural hazards, until there's a functional unit which is ready to be assigned to that instruction. It may not have all of its operands yet, but there's a functional unit that can be assigned, and in fact in the entry for the functional unit table, as we'll see, it will make a record of that instruction and what if its operands are ready and what if its operands are not ready. So we've avoided structural hazards in the instruction decode stage by stalling decode and all instructions behind it if there are any structural hazards. That's one point at which this algorithm is a little bit less than optimal. The other hazard which is decoded early is the write after write hazard. If there is an instruction which is already recorded as writing a result to a particular register file, we will not issue into the scoreboard another instruction that has that same register as a destination. So we get rid of write after write hazards early on. But the other hazards, the so-called real true data dependencies, the read after write hazards, are allowed to exist in the scoreboard, and basically the instruction hangs around in the scoreboard allocated to its functional unit until all of its operands are ready, until all the read after write hazards clear. At that point it reads the operands from the register file. Notice that the operands are coming out of the register file, so they must have been written back there by any previous instructions producing those results. Then it goes into execution, produces its result, and then it's ready to go into write back. But now it has to watch out about write after read hazards. Notice that this functional unit may be producing floating point register 0, but there may be another functional unit that hasn't gotten started yet, another instruction in the scoreboard, that's waiting to use the old result of floating point register 0. This instruction, although it's finished, can't write its result back into floating point 0 in the register file until all instructions waiting to begin execution in functional units have read their input operands. So the stall for write after read hazards are occurring in the write back stage. Let's go over an example and see, in fact, in a pipeline sense, what happens. Let's say we have a multiply instruction. It's going to take 4 cycles. We can get it started right away. It goes through instruction fetch, instruction decode, scoreboard stage. It can be issued immediately. It fetches its operands from the register file, goes through its 4 stages of execution, and write back. Now the next instruction coming along, the stall, notice, has a true read after write dependency on FP0. So it can get into the scoreboard, but in fact it can't get into execution. In fact, it can't even get into register fetch until the previous instruction has written its result back. So these stall cycles here, these 4, 1, 2, 3, 4, 5 stall cycles within the scoreboard represent the read after write hazard for FP0. Now notice there is no forwarding going on here. We could have, in theory, gotten this going at least a cycle earlier, or maybe 2 cycles earlier, well, probably a cycle earlier, or 2 cycles earlier, by forwarding from execute to execute, the way we did before. In fact, most of the original scoreboarding implementation didn't do that, and in fact forwarding doesn't quite buy you as much as it used to, because instructions now omit steps that they didn't need to. We don't have to wait through a memory step, for example, for units that don't use it. We don't have to pad out short instructions to fit longer pipelines, because each instruction takes a variable amount of time going through its pipeline. So forwarding is not as important in a scoreboarding-like scheme, although if you were willing to devote the extra hardware to it, you could get some additional performance benefit. Okay, what happens with the following add instruction? Well, the following add instruction can execute. It goes into the scoreboard unit. It has no functional unit dependencies. It has no write after write dependencies. It can execute, but then at the end it has a write after read dependency, because the store instruction hasn't yet gotten into its register file stage in order to read the result of, to read the value of register 4. If the add were to proceed, it would destroy it prematurely. So in fact, the add has to do 2 stall cycles waiting to get into write back until the store has at least gotten through register fetch. So this represents a write after read hazard. And finally, the negate instruction is a quick instruction, but in fact, it's about to store into floating point register 0. It, in fact, has a right after right hazard with multiply, which is still in execution. So it can't even get into the scoreboard. It has to delay 4 cycles in instruction decode, in fact, backing up all instructions before it, waiting for the right after right hazard to clear, waiting for FP0 to be written by the multiply instruction before it can get into the scoreboard. Now, this is probably not the best you can do. There might be better schemes for clearing right after right hazards, but this is what the traditional scoreboarding scheme does. Make sense? The next page on the slide basically shows the data structures that the scoreboard needs to maintain in order to keep track of what's going on. I think what I'd rather do is skip ahead a couple of slides and show you basically the same data structures with a bunch of instructions filled in, indicating what the current status is. There are 3 tables that the scoreboard has to maintain. One is for all of the instructions that are issued to the scoreboard. Remember, that means that they have no functional unit hazards and no right after right hazards. It needs to keep track of the instruction. It needs to indicate whether or not it's been issued. It has to keep track of whether or not its operands have been read, which means it could go into execution, and whether or not its execution is complete. And as soon as its result is written, then that entry can be removed from the instruction status table. For each functional unit, it needs to keep track of whether it's busy, what the detailed operation is, what the destination register that functional unit is going to modify when it's finished. And then for each of the sources to that functional unit, it needs to keep track of what register that source is, and whether or not that register, that source register, is the destination of some other functional unit. So in this case, for multiply 1, it says that one of its source operations is register 2. Register 2 is in fact the destination of a previous instruction executed by the integer unit. And here the assumption is that the loads are executed by the integer unit. So it says that register 2, which the multiply needs, is not ready, and we're waiting for the integer unit to provide it. Register 4, on the other hand, is not coming from a functional unit, and it's ready. It's ready to be read out of the register file. So in fact, instructions hang around in this state until something happens to make both of those ready columns 1, at which point it can read the registers out of the register file and begin its execution. The other table that the scoreboard has to keep track of is for each of the registers which functional unit is about to provide result to that functional unit. In fact, this duplicates information which appears in the functional unit table, but it's indexed by register number. So it makes a very quick way for the scoreboard, for example, to detect right after right hazards before it issues an instruction into the scoreboard. You can just check the entry for the destination register for the new instruction to see if there's something in the register result pending file or not. The book has a rather complex sort of pseudo-mathematical description of what all of the rules are for getting instructions issued into the scoreboard and getting instructions executed. What I tried to do in, I guess what is now the previous slide, is to describe that in sort of pseudo-English. And you're welcome to read either this description or the more mathematical description in the book in order to get a sense of exactly what has to be done. Let me go point out a couple of interesting parts. The first is that during instruction fetch, it checks for the two hazards that we said would block entry into the scoreboard. One is to see if the functional unit is busy or not, and there's a column in the functional unit table saying whether it's busy, so that's easy. And the other is to see that there are no other results pending for the destination register of that instruction. All it needs to do is look up in the result register pending table to see that there's an entry in there, and it knows that there's a conflict and can't issue that instruction. Once it passes that, it then assigns that instruction to a functional unit and fills in the fields. For the operand fields, it can fill in ready to be true only if there's no functional unit which is pending for that register. So again, it looks at the result pending table, and if there's anything in there, then it says that that operand is not ready. If there's nothing in there, it says that there's no current instruction which is going to produce a result for that register, so we can mark that operand as ready. Haven't fetched the operand out of the register yet, but we can mark it as ready. Then when both registers become ready, we can begin execution, dispatch the instruction. We set ready equal false for both of those source registers, and we'll see why in a second, and read the registers out of the register file and start execution. Now the interesting and complicated part of this algorithm actually occurs in the write-back stage, because that's where multiple operations have to be done. First of all, when a unit finishes execution and is ready to write back, you've got to check that none of the functional units need to use our result register, which is to say none of the functional units has our register listed as a source and ready false. That's the case where there would be read after write hazards. So this has to essentially be an iterative search over all of the functional units. In fact, what it is a parallel comparison among all of the functional units to make sure that our result register is not listed as a source for source which is not ready for any of the instructions awaiting execution. Then if that's true, you are ready to do the write back. So we can write back to the register file, clear our functional unit status, making it ready for somebody else, clear out our destination register result pending, saying this register is no longer a destination for any instruction. But also we have to make ready any functional units that are waiting for our result. So any functional unit that has our, in the source column, that has our functional unit listed as a source and not ready, we are about to make ready. So you can make that ready, and then that instruction will be able to issue if both of its source operands are ready. So the write-back decisions are complicated and require a fair amount of logic because there are multiple parallel comparisons and operations on all of the entries in the functional unit table. In fact, the functional unit table is hardware that's replicated. It's not sequentially accessed. So all of those decisions and update operations can happen simultaneously in one cycle. Questions? It probably makes sense, if you're confused about how this works, to start with a state like this and take it one or two cycles through the execution. The next thing that's going to happen here, for example, is that the load instruction is going to finish. Its result is going to get written, which means that the two instructions that are waiting for F2, which is to say this one, waiting for the integer unit to provide F2 and it's not ready, waiting for the integer unit to provide F2 and it's not ready. When that instruction goes into write back, it will change both of those to yeses. They will both, in fact, be ready to begin execution, and it will mark FP2 as no longer a destination. As a result of that, as soon as the load finishes, we've got two instructions that begin execution in separate functional units simultaneously. It probably makes sense for you to try to go through a couple of stages of this to understand in detail how it all works. So let's summarize. What has this scoreboarding gained us? Well, it allows us out-of-order execution and out-of-order completion for instructions that don't depend on each other. We can now execute instructions, begin execution of instructions, even though previous instructions have not been on execution. It centralizes all of this decision-making in one place, the scoreboard. And although it sounds complicated, In the 6600, the scoreboard was about as big as one of the functional units, and it had, I don't know, 6 or 8 functional units, so it only added an additional 1/6 in overall complexity to the machine, so it was certainly worthwhile from that point of view. But notice that we've got all of the functional units talking independently to the register file. So we need lots of register file ports, or we need lots of buses to and from the register file. Additional hardware in the interface between the register file and the functional units. Notice also that I said that there wasn't any forwarding. All operands come from and go back to the register file. There's no intermediate buffering. There's no bypass pads. One could add it to scoreboarding and get some additional performance, but as I noted, because we've now optimized the pipeline for each instruction to not go through cycles that it doesn't need, the benefit of adding forwarding is only 1 or maybe 2 cycles, and not multiple cycles, even for very long pipelines. The other disadvantage is that we still have write after read and write after write hazards. These naming dependencies where registers get reused, and we could avoid it if we had used a different register, still doesn't get solved by this. We could solve it in software by using register renaming. But there is a technique, which we will discuss next time after the midterm, for hardware which enables you to get around these hazards without doing any extra software. That's all for today. Remember the review session tomorrow. Have fun with the midterm.